Okay, everyone, thank you for joining our webinar on scratch and defect analysis. I'm Abby Lindbergh. I lead GelSight's applications engineering team. And just a couple of items before we get started. We will be recording this and posting it to YouTube after the session. And we also will have the Q&A active throughout. So we have Frank Chang from my team answering questions live throughout the session. And then we'll have plenty of time for Q&A at the end as well. So with that, I will hand it over to Thierry Montel to introduce himself and start the webinar.
Yeah, thank you, Abby. I'm Thierry Montel, so in charge of the distribution network of GelSight and also some key accounts, especially in the aerospace industry. So welcome to anyone, and thank you very much for participating to this webinar on this Friday. So the launch of GelSight Modulus last month has really triggered an enthusiastic and very positive reaction from our customers. And with this new member, GelSight propose a unique family of products able to rapidly and accurately characterize any surface defect on any material and almost on any complex shape, including bores. And this is the great advantage of the 90-degree angle of our modulus. And it appeared very timely to us to dedicate this webinar on the workflow from the detection of surface defect to its full characterization and its reporting. We will describe the different steps of the workflow of a classical quality control operation, the way you do it, in your company, and also to show you how rapid, how fast can be a measurement leading to a final report. Yeah, surface defects such scratches, dents, pits need to be well analyzed. This is really needed because it can be related to the understanding of their origin in a manufacturing environment with the objective to define corrective action and also to reduce your non-quality costs, and this is very, very critical for you. And also it can be, fundamental to precisely quantify a damage in order to verify the integrity of a part and to ensure its mechanical resistance and mechanical properties. This is especially crucial in critical industries like, aerospace, nuclear energy, chemical installation. It may be surprising, but the characterization of these surface defects is often a challenge. A challenge because of the optical properties of the surface you want to control. The surface can be shiny, can be opaque, can be transparent, of different material. You can have carbon fiber plus resin. You can have transparent acrylic. So there are different challenges, in front of the parts you want to measure, and also challenge due to the access to the area to be controlled. I was visiting yesterday a customer having very specific measurement to do, and the modulus system was the perfect tool to do so. So we are really bringing something unique. And also in many cases, these difficulties necessitate to take molds of these defects, these scratch. This is something which is really well, developed in the industry, but it is time consuming and it's rarely, giving you accurate and repeatable measurement. And on top of that, the traceability of this mold is something which is difficult to ensure, and it represents another challenge to manage that, in your quality management system. So in the following demonstrations, Abby will enter into detail of the use of the different functions of GelSight Mobile, our software, using the Series 2 system and also Modulus. You will see that we have highly simplified the workflow to take a measurement. The switch from one probe to the other is extremely simple and extremely fast. And you will see that the ensemble of our family of product, Max, Mobile, Series 2, and Modulus brings really a great improvement in terms of efficiency, in terms of workflow. So enough talking now, and let's let the place to Abby to demonstrate our product on the real cases.
And thanks, Thierry.
Thank you,
So
Abby.
I think I'll start with the overview of how GelSight works. And I've got our Series 2 system here, as well as our Modulus system. So I'll hold both of them up here. And the way this works is we've got one button that we click on the system. And when we click that button, I'll take this out so we can take a look. We're actually taking 6 images, one with each one of these banks of LEDs illuminated. I'm going to share another slide to help illustrate that. But basically, we take these 6 images with the 6 different lighting orientations, and we use a process called photometric stereo to get a normal map and a 3D height map from that. And I'll hold the modulus up as well to show you what that looks like without the gel as well. So you can see we've got the same sort of technology inside. We've got our lens and camera and our illumination system at the end, taking the same series of images and some additional ones for image alignment for this. So I'll just lock that gel back in there. But this works in conjunction with our gel sensor. So we've got our gel here, and this is what's conforming to the surface. So we're making contact with the part. It's really soft gel, kind of like your fingertip. And it also has a pigment layer on it. And the pigment layer is what lets us look at the surfaces regardless of their optical properties. So like glass, metal, textile, all looks the same to us. So we don't have to do anything different in our software to switch between materials. We're looking at everything through the other side of that pigment layer. So with that, I will pull up, I'm going to stop sharing the slide here. And I will change my video so we can see my desktop here. And then I'll share our software. Let me switch my camera. Here we go. There we go. Now we can see the desk over here. All right. And before I start sharing my screen, while this video is a little bit larger, I'm going to hold up the sample parts that we're going to take a look at. So the first one that we'll look at is the piston that we have here. And we've taken a look at some of the defects inside of this bore before, which we'll look at again. And we're also going to flip it over and take a look at a defect inside of the bowl of the piston on the top here. And then we also have our classic example of defects on the edges of blades, which is a big application for us. It's really challenging for a lot of other measurement systems. So I'm going to share my software screen, and as I do that, if you need to switch between which one is your main video, it'll automatically make the software larger, but you can click on the video display if you want to see what's going on the tabletop while I take the scans. So click between the two to switch between whatever the main view is. So let me share my screen now. Go here, and we'll go live. And the first thing that I'll do, I'll just press my fingertip into the top of this so you can get an idea of the resolution of the system. You can see my fingerprint right there. And we'll take a look at the blade example first. So as I go through these scans, what I'm going to do is I'm going to take the scan and then walk through the analysis and the PDF report generation. And then we'll go back and we'll talk in a little bit more detail about how the analysis worked so that you can see kind of the start to finish workflow from taking the scan and generating the report. And then we can talk in more detail about how we did what we just did. So the first one, we're going to take a scan of a defect on the edge of this blade here. So I'm just going to press the gel onto the side here. I see that defect there. And we'll measure that. Just click the button one time to take the scan. And now the 3D data is generating. And once that's available, we'll click the scan to open that up. And we like to use our offset function to measure defects on edges. So I'm just going to come in here and take a profile measurement of this. And I'm going to add my reference surfaces on either side of my defect. And I'm going to configure my measurement to measure the minimum point compared to the average of my reference surface. And I have my result, and I'm ready to generate the PDF report that goes with this. So we can see in the top left corner here, we've got the offset that's being reported, about 106 micron. And we can also customize this PDF report. So really, if we want to see that defect more, we can zoom in on it, spin that around however we want to see that. And same with the 2D view here, we can pick how we want to view that as well. We can customize this with notes, and we can customize this with a logo. Right now, obviously, it has the GelSight logo. Maybe next time I'll put the webinar title there or something like that. But all of that fully customizable for adding to whatever system you need to upload your report to. And now I'll go back to analyze and talk a little bit more about what we just did, since I kind of clicked through it pretty quickly. But let's look at the scan in 3D again here, so we can see the detail of that defect. And we could even increase the scaling to see that, to enhance it and see that a little bit better. See that defect there. I'll jump back to analyze now. And the way that the offset function works is we drew this line. We drew this line and we were able to see the profile of that surface. We then had to tell it where our reference surface is. So this is a handheld tool. You might not be perfectly perpendicular to the surface. And that's totally fine, because we are going to accommodate for that in all of our analysis functions. So with the offset function, that is handled through what we call leveling. And leveling in this case, I added 2 levels, one on either side of my defect. This is basically adding your reference surface, your levels, your 0, however you want to think about it. But really, I just added 1 on either side here, because those are my 2 reference surfaces. If I had a step height, maybe there would just be 1 and it would be the top of the step, for example. If I had a sawtooth pattern, maybe I would have 5 and it would be the top of each tooth. But that's basically what we're using to define where our reference is. And then we have our measurement regions that can be configured with minimum, maximum, or average for each one of them. So I took the average of our reference surface and measured the minimum point with respect to that. So this is a very common application for us, because defects on edges are typically challenging to set up with a lot of other systems. The ease of just pressing the gel onto the side of this really makes a difference for a lot of our customers. And I'm going to go back to Capture, and we're going to take a look at a new feature called auto offset, which is an enhancement to offset and a direction we want to keep moving in as far as software development. So we should see more improvements on this along the way. But let's take a look at what auto offset can do to automate this. I'm going to take a scan of another defect on this blade. You can see this one here. And maybe we'll look at that defect there. And I click the button to take the scan again. And our 3D data is generated. So we'll open it up. And I'm going to open a function that I named auto offset. And we'll talk a little bit more about that in a second. I'm just going to draw my line here. And you can see it actually added all of my regions automatically. And I can generate the PDF report from here. So we can see this one here, like that. And measuring about 176 micron for the deepest point along that profile. So I'll go back to analyze and talk a little bit more about what auto offset is. And what I have here, I named it auto offset, but really this is just a variant of offset. So within our offset function, we have an option for this auto offset checkbox. So I just have our offset function with the auto offset checkbox enabled, and that allows me to just click and drag. And auto offset is going to automatically populate your levels and your bottom and top measurement regions to try and basically figure out what you're trying to do without you having to tell it what to do. So we really want to keep improving the automation here. Right now, this is really for flat surfaces, not for curved surfaces. We don't have control over the level order of this. But we're planning on building upon that for future versions. But auto offset for defects on edges is really like the introduction of minimizing the clicks that are required for the current offset function. So I'll move this sample out of the way now. And we just went over offset all of these applications for defects on edges. That's my typical recommendation for when you use the offset function, be basically step heights and edges, defects along edges, because we have other analysis functions that we use when we have defects that have some area around them. So for these, I'll actually go over to capture, and we're going to switch over to our modulus system. I'll put this here. I'm just going to unplug our Series 2 from the tablet, and I'm going to plug in our modulus system. So you can see that lighting up, and we'll see it connect in just a second here. So we're already ready to use our modulus system. All I did was just unplug the USB-C port from the USB-C cable from the tablet and plugged in the modulus one. So pretty quick churn over to be able to switch between the systems here. And now let's take a look at a defect within the bowl of this piston. So this is an example of something that Series 2 might not be able to access. It could access some of these on the top, but if we have a defect maybe further into the bottom of this bowl, then it's going to be something that we need a smaller gel, a smaller probe to access. So that's why we have the modulus system. So I'm going to go in and I'm just going to press onto the surface here, and we can see that defect. I'll take that scan. I'm going to hold it at an angle so you can see a little better. Maybe I'm blocking it with my hand. It's a little bit better there. And you can see that live view. And this is an example of a complex geometry. So we're going to talk about the scratch function, but you can see this has kind of a cone shape to it. So it's not a flat surface, and it's got some curvature in multiple directions. I'm going to open up that modulus scan. And the scratch function has an input of 2 shapes. So I'm just going to click on this, and I'll walk through adding these shapes and generating the PDF report, and then we'll come back and talk about it a little more again. So something like that around our scratch, and then something like that around that for our reference surface. And we get a blue dot for the deepest point, about 25 micron. And then we can turn that into our PDF report. So we can see that geometry of that surface. And maybe we want to zoom in on the defects, we can see that larger in our PDF report. All right. So I'll go back over to analyze and talk about what we just did. So the scratch function, it can be used on flat surfaces, curved surfaces, complex geometries. It's really a very versatile analysis function. So the first step we did was we drew a box around our defect, and that's basically your search region. It's going to pick the minimum and maximum point within that first shape, within your first shape that you drew around your defect. And then the second shape we use for our reference surface. So we take what's outside of this first shape and inside of the second one and fit a reference surface to that. It's a 4th order fit, so that's why we can handle these complex geometries as part of this. And then your depth and your height are going to be with respect to that reference surface. So we can see if we zoom in here a little bit, this blue dot is our deepest point, and that red dot is the tallest point. It's the maximum height on that burr that we have there. So the scratch function, definitely great for complex geometries. We also have our defect detection function, which is great for flat surfaces, and is even more automated than what we see with the scratch function. Defect detection, we're going to draw 1 shape instead of 2 shapes. And for that, I'll switch back over to capture. And for this one, we're going to take a look at the defects in the bore. So for this case, I'm going to switch over to the 90-degree lens. So for that, move that out of the way so you can see it on the video. I'm going to disconnect this locking ring here and drop on our 90-degree lens and lock it in place. So we should see it connect in just a second here. Once I'm done turning that, there we go. So for defect detection, and for this, I'm going to take a look at one of the defects inside of this bore. So we'll come in here. You can see that one in that corner here. Slide over. We'll take this scan here. Actually, I'll hold it this way so you can see on the video the access to this. So something like that. All right, so same as we just went through with the straight lens and with series 2, our 3D data generates, and we'll open that scan up. And for this, let's use defect detection. You can see I've got a box drawn here, and I'm going to click Analyze. And we're going to get the characteristics of the defect and the profile through the deepest point, and then we can turn that directly into our PDF report. I'm going to zoom in on that defect there. And we'll jump back over to Analyze to talk about it a little more. So you might be thinking, hey, this is the curved part, and you just said only use defect detection on flat surfaces. And that's true. So when we're looking at a surface with the Modulus system, we're looking at such a small area that sometimes we can use defect detection even on curved surfaces. And it's the same with series 2. It just depends on the radius of what you're looking at. So since we're looking at sampling such a small area, it needs to be a pretty small radius to be considered, really a curvature for the analysis function. And the defect detection function actually automates very nicely as well. So all of our analysis functions have this pencil icon here, and I'm able to click Set Defaults. So if I'm happy with my configuration, I can start to automate the defect detection function. So with that automated, I can go into Capture and run my analysis from here. And you know what, actually, before we capture some more scans with that analysis, let's set up some pass-fail criteria for it as well. So I'm going to go to Configure and select Defect Detection. And maybe I care about the depth, and I want to add a pass-fail tolerance on this. We'll put it in as 10 micron here, but this basically says any value of 10 micron or lower for the defect will pass. And now we'll go to Capture, and we'll say we want to run a routine, and defect detection is selected. You can pick any of your analysis functions that you've configured with the Set Defaults button. So now I'm going to come in here, and we could take a look at that defect. Again, we've got a nice piece of fuzz on the part there too. So we'll take a look at this defect, or maybe even one on the other side that might have seen in the other webinar if you joined us for that. Take that scan as well. And when we configure to run a routine, we're actually doing the analysis now as opposed to doing the analysis at another after the fact. So we can see we've got this red circle here, or this red outline, and we can see that this failed. So we've got a depth of 25 micron here, and we can see the depth value of 25 exceeds the upper limit of 10. And when we open up the PDF report, we can see that message here as well. Depth value of 25 exceeds upper limit of 10. And one of the nice things about the PDF report generation, and this is a feature that we added recently based on a lot of feedback from customers, is the ability to export PDF reports as a batch as opposed to saving them off individually. So for a while, we only had the option to save them individually, but I think in 4.1, maybe that's when we introduced it, the ability to save them as a batch instead. So we could come in here, and maybe I want to save these two PDF reports, and I could select if I want to save them as a merged report or an individual report. And the merged report would put them into the same document. So I'll just click, I'm going to save this off here. And I will stop sharing, and I'll go ahead and find that to show you what that PDF report looks like. So let me find that and open it up. All right, we've got that. And now I'm going to share that screen, show you what that report looks like that's been merged. All right, so we can see that this PDF report includes that first defect and that second defect as well. So if you've got multiple defects on one part, you can include that all in the same PDF report now. So I'll stop sharing here. And I'll just kind of summarize when to use one function versus another function, because we just talked about 3 different ways to measure defects, right? So the first one would be using the offset function. We're really going to recommend using the offset function for edges and step heights. And then the defect detection is going to be for flat surfaces or surfaces that look flat enough to the system. And then finally, the scratch function for any kind of complex geometry as well. So maybe, Thierry, could you talk a little bit about the value that GelSight brings to these scratch and defect applications?
Yeah, sure. The very obvious first thing is that, what we can conclude is that from the demonstration, it's the part which goes to the lab which goes to the part, and not the part which goes to the lab. It's really now absolutely possible to measure a wide range of parts with our family of products, especially Series 2 and Modulus, which will evolve in the future. So there will be more and more use cases which will be addressed by Modulus, and this is a first tremendous value. You don't need to have a very sophisticated equipment in a lab. You have the lab really close to the part, and we have customers, for example, manufacturing landing gears. So if you want to bring a landing gear in a metrology lab, it's not so simple. It's not a compressor blade or a piston. And the fact to be able to bring the lab to the part is a very significant plus for these kind of manufacturers. The second thing, and you demonstrated it very obviously, is the simplicity and the rapidity of the tool. Just in a couple of minutes, you are able to take a scan and to have the report. And to my knowledge, it's really the only tool on the market able to do this kind of thing and to have such performance. If you take the case of the use of molds, putty material, the fact to prepare the putty, to take the mold, to wait for the curing of the mold, to remove the mold, to cut it, to go to the metrology or under a microscope, you need at least 30 minutes, at least. And with GelSight, you just need 1 or 2 minutes. So there is already a factor of at least 10 to 15 between a classical workflow using putty material and GelSight. So it's when you have dozens of molds to do every day, this is really something which brings a very significant value. We mentioned many times the fact that GelSight is totally independent on the optical properties of the material, but this is also very important when in maintenance operation, when you want to do measurement from aluminum, titanium, carbon fiber plus resin, transparent acrylic, you don't need to recalibrate your device each time. So you can, with the same calibration set of calibration with the same tool, you can do those measurements on many different parts and different materials. Our customers, they just prove by themselves, the accuracy, the repeatability of our tools, our systems. So there is no doubt about the accuracy and the validity of the measurement we take with our system, and it's a perfect communication tool between people on the shop and people in the design office or technical department wanting to have detailed information about a defect, about a dent or this kind of thing. And last, which is not the least thing, is the traceability aspects. So the fact that to be able to generate a report just by clicking on a button and saving these reports into your quality management system brings really, once again, a tremendous value. So your workflow are really, really squeezed and, just reduced to their simplistic, expression. So for me, it's really, the main value of GelSight. Just a last point, a few releases ago, we launched our API module, allowing you to, integrate GelSight into a fully automated environment, with an Internet of Things, sensors or Internet of Things environment. There is not only the possibility to integrate it mechanically, but also, on the software viewpoint, and you can remotely take control of the camera, remotely take a scan, and transfer the resulting data to your own, server, your own system. So this is summarize, the main points I see regarding the value brought by GelSight to our customers.
And Thierry, what about who cares about measuring scratches and why do they need to do it? Maybe kind of tie that into how GelSight can help with that, right?
Yeah, it's an interesting question because sometimes, there is some scratches, they are barely visible. When you take a part and you look at them, you almost don't see, these scratches. But we need to, people need to be very, very careful on that, because for me there is two reasons. First of all, a scratch or then can have, cosmetic impacts on the product and the perceived, quality. Nobody likes to have, a scratch on our car or a scratch on the screen of a mobile phone. It's human. So it's a first reason, and our customers they use GelSight to understand how this defect occurred on their product, to bring corrective actions and to reduce their non-quality cost. And there is a second reason for which I'm more familiar, especially in the aerospace industry, is that these tiny dents or these tiny scratches can become cracks, micro cracks, which will propagate due to thermal and fatigue, thermal and vibration fatigue, and this can lead to the the failure of the part. And when an aircraft engine lose a compressor blade or fan blade, you can see the results on on some or some photos, videos on YouTube or on social networks. It's pretty scary. Even if the engine has been qualified to resist to this kind of event, it's never a good a good thing to. So it's the reason why aircraft manufacturers or engine manufacturers want absolutely to avoid this kind of failure. So this is for me the two main reasons why scratches and dents, surface defects needs to be really carefully analyzed.
Thanks, Thierry. So I think we'll wrap up here, and we'll get to any questions that have come in. So feel free to add your questions in the Q&A right now. You might have to click more to get to it in Teams. It might be a little hidden, but go ahead and submit any questions, and we'll also post this to YouTube. So just another reminder about that. All right, it looks like we have one question that was asking if we could measure the radius at a bottom of a defect. So we do have applications where we do that. We do have a radius function. Let me see, I could open up one of those scans and show you what that looks like. Let's open up.
Yeah, very good question, and it is totally related with my comment about the initiation of cracks at the bottom of a scratch. This is perfectly illustrating the criticality of qualifying or characterizing a scratch.
All right, I'll just share my screen here too. So we have a radius function for this. I'm basically going to draw a line similar to how we did with the other functions. And I'm going to fit where I want to measure the radius. So I could come in here. We'll zoom in on this graph a little bit so you can see it. I'll check this. But we can see we're fitting a curvature to this spot on the radius. So I'm going to actually make this a little smaller and say I only want to fit this tighter spot here. You'll see it displayed as an ellipse in this case, but it is fitting a circle. And you'll see the center radius being reported here, this 127. So we know that we have, like just as Thierry said, this could be the signal that we're going to have a crack develop here, as opposed to just a scratch.
And typically, the 3D map of these defects can be sent to the technical department, and they can start to do stress analysis with the other tools, not GS Mobile, but with other tools. So it's really once again a wonderful tool and a wonderful tool for exchanges between the people which are on the ground and the design office or the technical departments.
Exactly. Just as Thierry just mentioned, we can export this as an STL file here. So you can go ahead and click that button and put that into another program. I am seeing a couple of hand raises, so I'm wondering if we're having trouble accessing the Q&A, but maybe we could find, if you go, I can't answer a hand raise. So if you find the Q&A button at the top of the screen, you should be able to access that and type your question in there. We see another hand raise, so I'm wondering if I see the Q&A, so hopefully everybody else can see the Q&A. I do have another question here about basically when to use the Modulus system versus the Series 2 system. And that's a good question. Basically, kind of the main trade-off is going to be your accessibility for your field of view. So what we're getting with Modulus is access to smaller spaces, and the Series 2 is really going to let you look at larger areas. So that field of view is significantly larger for the Series 2 system than the Modulus, which I guess I could pull up a diagram of that as well.
And you can switch from Series 2 to Modulus in just a few seconds. So this is really something which is extremely flexible.
All right, so here are kind of the differences for access to consider. So we can see the Modulus on the bottom left side here, and with the 90, and then we've got the field of views, kind of comparing them between Mobile Max and Modulus. Stop sharing here. All right, so I don't see any questions in the Q&A, so I think we'll wrap up here, but I know we're having a lot of people raising hands, so I'm going to assume Teams technical difficulty here. So feel free to send us questions to info@gelsight.com or support@gelsight.com, and we'll make sure that we answer any of your questions. And I think we'll be able to reach out based on who raised their hand here as well. I'm assuming we can see that. So thank you all for joining the webinar, and we'll send a link out to the recording so you can share that with anybody that might have missed it.
Yeah, thank you everybody, and have a nice weekend. Thank you very much.
Thank you.